All right, we're going to start section 5.3 by doing another proof. We don't really prove a lot of things, but I felt like this was something that needed to be seen. So we're going to look at Cauchy's theorem, which might be one of the most important theorems in complex analysis. And what it says is, as our hypotheses, we have an analytic function in a simply connected domain D. I'll explain this term in a second. Um, and that the derivative is continuous in D. So it's analytic, so the derivative exists, so we further demand it's continuous. In fact, being analytic will tell us that the derivative is continuous, but we've not proved that yet. So in fact, that condition is actually not necessary, that extra condition. What's the conclusion? The conclusion is then for every simple closed curve, contour, I guess we say, in D, C in D, the integral over C of f of z dz is 0. So that's the conclusion. That's what we get from the Cauchy's theorem, or sometimes called Cauchy's integral theorem. Now, what does simply connected mean here? So I'm going to draw you a picture here of something that's not simply connected. Actually, we want to do something. It's got to be a domain, so it has to be open. So our boundary lines have to be, open. So this guy is missing these holes. Make them a little bit more pronounced here. It's missing these holes here. And so since it's missing these holes, this is an example of something which is non-simply connected. Said slightly differently, we can draw a simple closed curve in our domain such that the interior of that simple closed curve has points other than the domain. Okay, so the interior of this curve that I drew has points not in the domain. Let's call this area this guy D, the purple shaded region, not in D. So this tells us that D is not simply connected. So what is an example of something that is simply connected? Well, it's basically an open, it's an open area in the plane, open and connected because a domain needs to be open and connected, but it doesn't have any holes in it. So an example of something that is simply connected is if I were to draw this shape and just shade in everything. Then any contour, closed contour you were to draw here would necessarily have only points in the domain inside of it. So this guy, let's call this D prime. This one is simply connected. As any simple closed contour only bounds points of D prime. So the interior of that contour only has points in D prime. So anyways, that's Cauchy's theorem. That's what simply connected means. And if you're analytic and your derivative is continuous, then the integral over every simple closed contour is 0 within the domain. We'll prove this in the next video, but let me point out why you need simply connected. So why simply connected? Simply connected is something that shows up a bunch when you take algebraic topology, if you ever get there. And well, the rabbit hole goes down as far as you want it to go, but uh, let's not go down that route. So uh, why simply connected in this setting? Well, we did an integral actually. We integrated over the unit circle the function 1 over z dz. So in that situation, what was going on? Well, we have sort of let me mark the origin maybe in red as a point that's not in our domain because we can't divide by 0. And then our domain was take C and then take out the origin. So the domain is everything that's not the origin. Okay, so in this case, D is C less 0. And the circle of radius 1 is a closed contour here, something like that. And notice the interior of that circle has the red point in it, and that red point's not in D. So let me point out here, D is not simply connected. In particular, the hypothesis of Cauchy's theorem is not true here. And in fact, we computed this and we found it was 2 pi I, which in particular is not 0. In contrast, suppose we were integrating, so as a separate example, suppose we were integrating over the circle of radius 1. I don't know, let's do something easy. Let's say the function z dz. So what is a natural domain for this function? Well, here we could take d to be everything, which is simply connected because you have all points. You're not missing any points. So it's sort of trivially simply connected. And then what is going to be the value of the integral here? Well, we parameterize it. We can parameterize with the standard one, where we let z be e to the it. So this is going to be e to the it. And then dz is going to be I e to the it dt. And this is, of course, on the interval from 0 to 2 pi. And then what? Well, let's see. We have integrals t 0 to 2 pi, I e to the, I guess there's 2it there. And let's see, if we integrate that, we need to sort of divide by the 2I. So we have integral t equals 0 to 2 pi, I over 2I. Oops, sorry. Yikes. I over 2I e to the 2it, evaluated from 0 to 2 pi. Let's see here, the i's cancel. So we have 1/2 e to the 2it evaluated from 0 to 2 pi. So we have 1/2 e to the 2I times 2 pi minus 1/2 e to the 2I times 0. So we have 1/2 e to the 4 pi I minus 1/2 e to the 0. Both of these values are 1 though, because this is a whole even multiple of pi. So that's a 1. That's a 1. So it's a half minus a half, and that's 0. Ooh, that was a little bit longer than I was expecting it to be. But here we integrated over a closed contour, and we indeed got 0. And in fact, if you were to integrate z over any closed contour, since the domain of z is really everything, it's an entire function, you will always get 0. You don't have to do the integral over and over again. You know, because it's a simple closed contour, that you get 0. Whereas in this case, the domain was not simply connected, and so we likely might not get 0. Okay, and we didn't. We got 2 pi I.